Hello, welcome to video 5.2b, which I recorded with no volume on at all. So now I'm starting over. More integrals yielding natural log functions. Okay, so as you know so far, we know the integral of cosine, sine, the integral, et cetera, et cetera, et cetera. But what you'll see missing from this list is what is the integral of tan and cotan and secant and cosecant. We don't have formulas for those yet. We just have formulas for integrands of cosine, sine, secant squared, cosecant squared, secant tan, and cosecant cotan. So what are they equal to? So here's what happens. These will involve ln's. Cotan is cosine over sine. So if I let u equal the denominator, which is sine x, then my du ends up being cosine x dx. So really, I can look at it as 1 over sine x times cosine x dx, which is 1 over u du. The integral of 1 over u du is the ln of the absolute value of u plus c. And u, of course, was sine x. So that's the formula for integral of cotan x dx. It's the ln of the absolute value of sine x. Tan is a little bit more difficult because tan is sine over cosine. If you let u equal the denominator, which is cosine, the derivative of cosine is negative sine x. So that negative is what causes a bit of havoc here. So we have to introduce the negative, counteract with a negative. We're left with negative the integral of 1 over u du, which is negative ln absolute value of u plus c. Now, some books will write the formula as negative the ln of the absolute value of cosine x plus c, because remember our u is cosine x. However, remember it's a logarithm, so a constant times a logarithm of something is the logarithm of that something to the power of that constant. This is not inverse cosine here. We're talking about actual something to the negative 1 is 1 over that thing, and that becomes secant. So it's ln absolute value of secant. So basically, and I'm not going to explain to you where these come from. That's very complicated. So these are the two different formulas we just found for the integral of tan x. Here's the formula for the integral of cotan x, and you can reproduce these two very easily. These you'll just need to memorize. Now notice they're all ln's of the absolute value. If you remember, derivative of secant was secant times tan. Well, the integral of secant is the ln of the absolute value of secant plus tan. And then cosecant, you just add a co in front of these, but it's a minus. Well, that's about the best I can tell you. Okay, so if we are integrating the tan of phi theta d theta, when there's trig, sometimes you'll let u equal the angle, sometimes you'll let u equal the whole trig function. Like back here, we let u equal the entire trig function cosine x, okay? All right, but here that wouldn't make sense because the derivative of tan of something would be secant squared and we wouldn't have the du we'd need. So we'll let u equal 5 theta. Du is therefore 5 d theta. Introduce the 5, counteract. I'm left with 1/5 integral tan u. And remember that formula was ln absolute value of secant u, but of course you can't leave it as u. You have to replace the u by 5 theta. Okay, so same idea here. You're going to let u equal the angle of the trig function, which is x over 2. Derivative is a half dx. You've got the dx. Introduce the half, counteract with the 2. You're now integrating. That's very confusing looking. You're now integrating. Let me do this. You're now integrating 2 secant u du, which is 2 times the ln of secant u plus tan u, absolute value, and then you replace the u's by x. Okay, so the integral of ln x dx, you won't learn that until BC. But interestingly, the integral of ln x over x dx, which at first glance would look to you like it's more difficult than this one, is actually easier. And that's an interesting thing about integrals. So what happens is, now you have to get creative. Obviously, there's no point in letting u equal x. There would never be any point in letting u equal x, because then it would just be ln u du over u, and it'd be the same thing. But here, if you let u equal ln x, and you remember to check for your duh, well, your du is 1 over x dx, which is exactly what the rest of this is, 1 over x dx. So really, if you just kind of rewrite it as ln x times 1 over x dx, you've got u du, which is, of course, u squared over 2 plus c, which is, of course, in our case, ln squared of x over 2 plus c. Over here, if you had ln to the 5th of x over x dx, you would let u again equal ln x, because this really means ln x to the 5th times 1 over x dx. And again, you have u to the 5th du, which is u to the 6 over 6 plus c. and then you replace u by ln x, okay? Um, be careful here. The ln of x to the power of 2 is the same thing as ln to the power of 2 times x, but not the same thing as the ln of x squared. Okay, solve the differential equation. Use the calculator to graph 3 solutions, one of which passes through the given point. Okay, so we're back to our separate the variables. So all you have to do is send the dx to the other side. Now, what you have is x over x minus 2 over x, right? Once I integrate both sides. So I have the integral of 1 minus 2 over x. So now you're integrating the 1 over x dx, which will give ln of absolute value of x. So we have x minus 2 times, and then when you integrate 1 over x, you get ln absolute value of x. Now, they did give us an initial condition here of negative 1, 0. So I'm going to replace the x's by negative 1 and the y's by 0. So replace the x by negative 1. ln of negative absolute value of negative 1 is ln of 1, and ln of 1 is 0. So it becomes negative 1 plus 0. I'm sorry, it's a 1 plus 0, which is 1. So now you know that you have this was your general solution, which I'm writing down here, but I'm simply replacing the c by 1. Evaluate the definite integral. Use the ti to verify. So you don't have to do the second part. All right, so this is one of those tricky ones. If you let u equal just the ln x, well, guess what the derivative of ln x is? The rest of it, 1 over x dx. So I'm going to rewrite this as ln x to the negative 1 times 1 over x dx, which makes you realize you have u to the negative 1 du. Okay, so I have u to the negative 1 du. I'm going to rewrite that as 1 over u du. Take the integral of it, and I'm going to have ln of absolute value of u, right? Because the integral of 1 over x dx is ln absolute value of x, so the integral of 1 over u du is ln absolute value of u. But I am integrating. I kind of left this drop, but I'm reintroducing here from x equals e to x equals e squared. So it'll be the ln of e squared, which was very clearly marked, minus the ln of e. Now, here's where you have to know your values, okay? The ln of e means e to which power equals e. Well, that's 1, okay? Then you have the ln of 1. Well, the ln of 1, of course, is 0 because, whoops, e to the 0 is equal to 1. Over here I have ln of e squared. There's a couple of ways to look at it. One, you can bring the 2 in front. You have 2 times ln e, which is 2 times 1 or 2. Or you can look at it as e to which power equals e to the 2. So it becomes 2, and you're left with ln 2 minus 0, which is lx over 2.